In this video, we are going to look at something called ionic compounds and ionic bonding. Before we get to that, though, we're going to look at some Lewis diagrams. Now, these are going to sort of result from our Bohr-Rutherford diagrams that we drew the other day, and they're going to make our lives a little bit simpler. So what they do is they indicate the number of valence electrons that an atom has. And let's not forget that if you want to know how many valence electrons something has, you just need to know the group number, because the group number tells us the number of valence electrons. So let's go ahead and draw an example from each group. So if you're talking about lithium, it's in group 1. It should have 1 valence electron. Feel free to use any symbol you want. I generally use the dots and X's to represent these valence electrons. Group 2 might be calcium. And group 2, so it has 2 valence electrons, and I like to put the valence electrons separated from each other because they're negative and they're repelling, so they probably want to get away far away as possible. Aluminum's in group 3, so it goes like that. Maybe not repelling as much, but I just like to, again, keep it symmetrical. And group 4 is carbon, and so it's got 4 X's around it. And now something changes a little bit when we get to group 5. So with nitrogen, what we do is we start to put our valence electrons around. And then when we get to the 5th one, we actually put 2 together right there. Those are called a lone pair. Sorry, my writing is bad. They're called a lone pair. That's sort of the goal of these valence electrons, is to pair up and form a lone pair, because a lone pair is very stable. They don't like to react. So nitrogen here has 1 lone pair. As we move on to sulfur here, it's got 6 valence electrons, and so I end up making 2 sets of lone pairs. And when we get to iodine, that's group 7. Notice that we now get 3 lone pairs. And then when we get to argon, it's all lone pairs. So this argon here is very stable. In fact, that sort of leads us into our next part here, is we want to talk about the stability of some of these things. So we have an octet rule, oct meaning 8, states that atoms are only stable when they either have 0 or 8 valence electrons. So if you think back, out of all the ones we just drew, only that argon, which was from the noble gases, has a full octet. And so not exactly, all the other atoms we drew are not exactly happy with each other. So for them to become happy or stable, they're either going to have to gain electrons or lose electrons, and that's what we're going to figure out now. So let's move on to that. So what we want to do here is we want to have our ions obeying the octet rule. So let's first start with metals, and you can pick any metal from group 1 you want, because they're all going to end up kind of being the same here. So let's look at lithium. It's group 1, so it has 1 valence electron. So we have to ask ourselves, for this to become stable, does it want to lose 1 or gain 7? And the trick here is we want to go with the lowest number. So we want to lose 1 electron. So let's draw that lithium. It now has lost that electron. And it's actually got a +1 charge, because if you think about it, it started back with 3 protons and 3 electrons, and really 1 valence electron is what we're interested in. And it booted that 1 off, and so it lost 1 electron. So it has to have a stable charge of +1. And then there's that 1 electron. So those are the same ones. Those are what I'm talking about here. And group 1, all the rest of them do the exact same thing too. So they all are going to form +1 stable charges. Let's look at group 2, calcium. Will it gain 6 or lose 2? And the answer is it's going to lose 2. And if it loses 2, it's going to have an overall charge of +2. And there are the 2 electrons it's lost. And when we get to group 3, something like aluminum, we ask ourselves, is aluminum going to lose 3 or gain 5? And of course the answer is it's going to lose 3, and if it loses 3, it's going to end up with a stable charge of +3. And we've made a little discovery here about metals. What we've discovered is that metals will lose valence electrons to become stable, positive cation ions. So soak that in for a second. All metals are behaving the same way. Now, it's a little tiresome to go on here and try to figure out all the stable charges here. But what I do want to point out is that our periodic table has these stable charges. So lithium, which is right here, number 3, if you look right there, it's got a little +1. That's its stable charge. You'll notice sodium underneath has a +1. Potassium has +1. Rubidium has +1. And even as we get into group 2 here, you'll see that they all have a bunch of 2's going on. So those are the stable charges. So let's talk about nonmetals and their stability. We've learned a little bit about metals and nonmetals, and they're generally opposites of each other, and that's exactly what's going to happen in this part here. So let's start with group 7. We're not going to worry about group 8 because it's happy, it's stable, it's got its full set of valence electrons. Chlorine. Chlorine's in group 7, so it has 7 valence electrons around it. So to make it stable, we have to ask ourselves, is it going to lose 7 or gain 1? And gaining 1 is the move. So we're going to write this a little differently. We're going to write +1. And then when we go to draw this picture here, what we're going to do is we'll write the original 7, and then we're going to, with a different symbol, put in that, to make that last pair. And of course, if we're adding an electron, it's got a -1 charge to it. So group 7 atoms are going to gain an electron to have an overall charge of -1. That will be their stable charge. As we look at group 6, something like sulfur that has 6 valence electrons, we see that it has a couple of spots for us to add some stuff in, right there and there. So we're going to add 2 valence electrons in. Boom, boom. And if we've added 2 electrons, it's got a -2 charge. And group 5, nitrogen here, it's got 3 spots for us to make some lone pairs. So we'll add in 3 electrons, giving us an overall charge of -3. So what you'll notice here is that the nominals have all done something similar. They have all gained valence electrons to become negative stable ions known as anions. And again, all of these are on your periodic table. So if you look at nitrogen, there's a little -3, oxygen is -2, fluorine is -1, and you'll notice that our noble gases that we didn't do anything to all have stable charges of 0. That we'll never use that 0, but there it is. So let's get on to ionic compounds and ionic bonding. So a compound that contains ionic bonds is known as, an ionic compound is a compound that contains ionic bonds. Ionic bonds are created when electrons are lost from a nonmetal and gained by a metal. So what we're going to be doing is pairing up a metal and a nonmetal. So these, like I just said, are made of metals and nonmetals, or a different way to say it is they're made of cations and anions. So let's use our knowledge of valence electrons here to draw what would happen if we put sodium and chlorine together. So sodium, there's sodium, it's in group 1, so it's got 1 valence electron. We're going to add that to chlorine, that's in group 7, and it has 7 valence electrons. So these are a nice pair because sodium can get happy by losing its 1 valence electron to have none, and chlorine can get happy by gaining 1 to get up to 8. So sodium has none around it. There's chlorine, and it has 8 around it. So both atoms have obeyed the octet rule, and both are now stable. So what we've discovered is when sodium and chlorine go together, you always end up with 1 sodium and 1 chlorine. We generally don't write those ones in. Now, if we want to name this compound, here's a refresher that firstly you would name the metal. So we've got sodium in this compound. And then secondly, you'll name the nonmetal with an "ide" ending. So chlorine becomes chloride. And we've discovered the formula of sodium chloride is always 1 sodium and 1 chlorine all the time. There's no other version of it. So this is about as simple as they get. Let's turn it up a notch here. Now I want to look at what happens when we put magnesium and fluorine together. So there's magnesium. It's in group 2, so it has 2 valence electrons. And we're going to add that to fluorine that has 7 valence electrons, but we end up with a problem. It starts off nicely. We can put that 1 valence electron right there, but then this magnesium still has a valence electron, so it's not down to 0. It hasn't followed the octet rule. Well, what can we do? Well, probably the simplest thing to do is just add another fluorine in, because we can take that valence electron and put it right there. And that's what we're going to do here. So when I go to draw this one, I'm going to put magnesium in the middle just to make this symmetrical. And there's 1 fluorine with 1 of those valence electrons, and then same thing on the other side. So that's one way to draw it. Maybe a simpler way to draw it would be without the valence electrons, just to draw sort of a stick diagram of it. And what we discovered is the formula here for magnesium fluoride, which is going to be the name. It's always made of 1 magnesium and 2 fluorines. So we use that 2 right there as a subscript to tell us what the formula is going to be. And like I said, this one's going to be called magnesium fluoride. Let's look at essentially the hardest one we're going to come across here, which is what happens when we put aluminum and sulfur together. All right, so aluminum, group 3, 3 valence electrons, plus sulfur, which is in group 6 and has 6 valence electrons. So they're not necessarily a great match. What we can do is we can take one of those valence electrons and put it there and put it there, and aluminum still has one left. So I think what I'll do is I'll add in another sulfur, and then we can put that one there, but then this sulfur needs another one, so then we'll add another aluminum, and then that one can go there, and then we got another sulfur, and this finally is working out, but it's definitely been a lot of work. In fact, when I go to draw this one, I'm not even going to bother drawing all the valence electrons. I'll just draw kind of the final result. It's definitely helped us figure out what the formula of this compound is going to be. It's going to be made up of 2 aluminums and 1, 2, 3 sulfurs. And to name this one, name the metal aluminum and name the nonmetal sulfide. So aluminum sulfide is our formula. But like I said, this method is becoming a headache. There's got to be a better way of doing it. And there is, and it's called the crossover method. Okay, so what happens with the crossover method is we go back to that first idea of our lesson, which was figuring out the stable charge of an element. So let's see what happens when we put this aluminum and sulfur together using this idea of the stable charges. So you got aluminum, you look up its stable charge on the periodic table. It's number 13, it has a charge of +3. And we've got sulfur, and if you look up its stable charge, it is -2. So we're going to use those numbers to tell us what the formula of this aluminum sulfide is going to be. So first thing you do is you write the aluminum. And I jumped ahead a little bit, sorry about that. That 2 is going to come down, and it's going to tell us that we get 2 aluminums. Now to figure out how many sulfurs there are, you go to the 3 that's with the aluminum, that one comes down, and you get the sulfur there. And like I said, it's aluminum sulfide. Al2S3. If we go back to the previous slide, you'll notice that after all this stuff here, we actually came up with Al2S3. So they proved to be they gave us the same formula. It proves to have worked. Let's try this with the one previous. In our lesson, we did magnesium and fluorine. We put those 2 together. So we've got magnesium and fluorine. You look up their charges. We've got magnesium with a charge of +2, and we've got fluorine with a charge of -1. Cross it over, you want to figure out how many magnesiums there are. Well, you go up to the number with the fluorine, that comes down, and it tells you that there's 1, but we're not going to write the 1 in. Just by reading Mg, it's understood that there would be 1 there. And to figure out how many fluorines there are, we go to the number with the magnesium, that crosses down, and it tells us there are 2. And our name would be, again, magnesium fluoride, MgF2. Going back to that previous slide where we figured it out, yeah, we got the same formula, so again, that checks out. And back to our original one, this one ended up being maybe the easiest one we did. We've got sodium and chlorine going together. Sodium and chlorine, look up their charges, +1 and -1. And a little note here, the more times you look up the charges, the more you perhaps remember that sodium is always +1 and chlorine is always -1. And when they're each 1, essentially it's like it's reducing down a fraction. It's just NaCl, sodium chloride. So 1 chlorine and 1 sodium. And again, that's what we figured out on that earlier slide. So let's go ahead and do some examples here. We've got magnesium oxide. Typically what you should be doing in this is you should be writing your ions. So magnesium, look it up, it's got a charge of +2. Oxygen has a charge of -2. Now just like our NaCl one, the previous slide we had, they each had a charge of 1, +1, -1. And same thing's happening here. They each have the same charge of 2s. So that's like a fraction that reduces down. MgO. Bottom line is when the charges are the same, you get 1 of each element. And just to prove that quickly, magnesium has 2 valence electrons and oxygen has 6. So you can see how they want to pair up, and you only need 1 of each. Again, to further that, what happens when we get aluminum and phosphide? You'll notice that they each end up with a charge of 3s, so you get 1 of each. And a little something weird that can happen is something like magnesium and carbon that go together. Magnesium is +2, and if you look up carbon, it's got a few charges, but it only has 1 charge of -4. So when you cross this one over, your first thought is, okay, we should get 4 magnesiums and 2 carbons. This is one of the few examples where we actually want to reduce these numbers down. And so they each kind of divide by 2. Bottom line is you get 1 magnesium and 2 carbons. This probably won't happen very often. It's very rare that you're going to have to reduce things down. But this is one of the times that you would have to. Now, what happens when we get a metal that has more than one charge to it? Something we call a multivalent element. So these are metals with more than one positive charge. These are generally found in the middle of the periodic table. Just to further this, if we say look at some of these ones here, like cobalt has a couple of charges, +2, +3. Iron has a couple of charges. Magnesium has like 5 different charges. Copper has a couple of different charges. So mostly these ones here have the possibility of having multiple positive charges. You can never have 2 negative charges, only multiple positive charges, and they don't necessarily all have positive charges, right? Look at silver. Silver only can ever be +1, or gold. Well, actually, gold has 3, so not gold. But anyway, there's an example. So how do we deal with these ones that have more than one positive charge? Like say iron. Iron could be +2, it could be +3. Well, we're going to use something called the Roman numeral method. So if we had to identify this Fe +2, we would call it iron 2. Notice the 2 is in brackets. And this one would be called an iron 3. So Roman numerals are used to indicate the charge. So why don't we go ahead and write down the 10 Roman numerals that we're going to come across. You can jot these down here. You'll know 1 and 1, 2 lines is a 2, 3 and 3. So it's probably a good idea just to record this down in your notes so you can refer back to it. I'm always confusing 4 and 6. IV, VI. Don't do that. So why don't we take to wrap this up here, we'll take a look at some final examples using some Roman numerals. So it's always best or easiest when the Roman numeral is given to you, like in this example, copper 1 chloride. You know copper has a charge of +1. There's nothing to look up. It's given to you right there. And we've got chlorine with -1. So for each one, that's just going to give us a result of 1 copper and 1 chlorine. What happens if I gave you the ions that were cobalt +3 and phosphorus 3? Well, maybe the easiest thing to do is the formula, since they each have charges of 3. That just gives us one of each. C(op). Now your names. Now, if you're not sure about cobalt, you go to your periodic table, you look it up, and you realize that it actually does have a couple of different charges. So when you do your name, you're going to need to include that Roman numeral in your name. Last one here is MnO2. So first thought here is that, okay, you uncross this one and you realize, actually, so that's a mistake. It shouldn't be Mg, it should be Mn. So let's pretend that's an N. So manganese has a charge of +2 and oxygen has a charge of -1. So you double check the charge of oxygen. Does oxygen have a charge of -1? No, it has a charge of -2. So what's happened with this example is it's been reduced to lowest terms. So we kind of need to unreduce it. So hopefully this should be not too difficult. If oxygen is -1, it just means we got to double it. So we got to times it by 2. And if we times that one by 2, we're going to have to times that one by 2. So you should end up with, again, that should be Mn, manganese, +4, and oxygen is -2. So now these are correct. So when you go to do your name, you get the manganese 4 oxide.